Alright. So now let's move on. Present value, our next topic. Present value is it's almost just compound interest, but looking at it from a different angle. And you'll see what I mean as we kind of move along. We're basically just going to start with an example. Suppose you had the opportunity to buy a box, call it like a safe or a whatever, and the box has $1,000 in it, but it can't be opened for 10 years. So how much would you pay for the box today? Would you pay $1,000? Would you pay more than $1,000, or would you pay less than $1,000? Would you pay more? Why?
Technically, because of inflation, it would be less.
Explain that. I think I agree with you, but
well, because things will cost more. Yeah. So that's just going to be less.
Does that make sense? You've got $1,000. You got $1,000 in the box. $1,000 cash. 10 years from now, you're not going to be able to buy as much with that $1,000 as you could today due to inflation.
You got to get that.
Right.
No. Like, imagine it were just 1,000 $1 bills. So, because of inflation, today you'd maybe pay like $900 or something. And it does depend. You were right what you said on what the market is, and we'll talk more about that. What if inflation were 0? Then would you just pay 1,000? I would argue that even if inflation were 0, you'd still pay less than 1,000 today, because all else being equal, you'd rather have the money now. So think of the designer jeans example. If you could buy a pair of designer jeans 10 years from now, or you could buy that pair of designer jeans today, all else being equal, you'd rather have them today, because that way you get use out of them now. You don't have to wait. And it's the same thing with the money, because you could use the money to buy any number of things, and you'd rather have those things now. You get the use out of them rather than having to wait 10 years to get the use out of it. So $1,000 in the future is not worth as much as $1,000 today, and that's true even if inflation is 0. Now let's try to quantify this. How much less would you pay for the $1,000? And the answer, as Jane said, that depends, and it depends on the level of interest rates. So let's suppose that you have a savings account that earns 5% interest compounded monthly, and rather than buy the box, you could take your money and save it and earn 5%. If you were to take D dollars today and earn 5% for 10 years, you would end up with $1,000. Solve for D.
Why wasn't it?
Like what formula? I did 1,000 equals P times 1 plus 0.05 over 12 to the 120. Oh, you did monthly? Yeah. Oh. Are we doing monthly or? Oh.
The point here is you basically have a choice between buying the box or saving the money. If you save the money, you earn 5% compounded monthly in your savings account. Or If you buy the box, all you get is the box, which gives you $1,000 in 10 years. So the question is, how much would you pay? Where you basically be indifferent between putting the money in your savings account or buying the box. You'd earn the same return. So what did you guys get if you're done yet? 16 cents. Same thing. So is this the equation you used? And then you solve for D. You get 607 16 cents. Very good. Jeffrey, is that what you got?
That is what I got.
Good. So what this means is that $1,000 in 10 years is worth $607.16 today, assuming that interest rates are 5%. And we basically, just a bit of terminology, we would say that $607.16 is the present value of $1,000 10 years from now. And this concept of present value it's just one of the most key concepts in all finance, because as you're going to see, basically every financial instrument, stocks, bonds, everything, involves some amount of future cash flow. And the goal, lots of the time, is to try to figure out what's the present value of that future cash flow. So basically all we did here was we said we have a $1,000 cash flow 10 years from now. What's the present value of that today? And this simple example is similar to a lot of math that you would end up doing when you're trying to determine the value of a stock or a bond or whatever. And we'll talk more about that. But generally speaking, the present value of a future cash flow is given by this equation. And you'll notice that this is basically the same as the compound interest equation. It's just been rearranged. And instead of using P for principal, we're calling that the present value. And instead of using FV for future value, we're calling that cash flow, as in future cash flow. You guys have any questions so far? Okay. We can also take this present value equation and rewrite it this way, where all we've done is we've just factored out the CF. So I'll write it on the board as well, so a little easier to look at. So the only reason to rewrite it that way is because that part in yellow is going to give us what we call the discount factor. And the way it works is whenever we have a future cash flow, we multiply it by the discount factor to get the present value of that cash flow. Okay, moving on to bonds. I didn't know that you were going to get an intro to this on the car ride before I made this set of slides, but
He really does. He needs the whole thing.
okay. Hopefully this will not contradict anything that you learn, and hopefully it will only serve to clarify. So what is a bond? A bond is like a loan. The amount of the loan, I should put that in quotes, the amount of the loan is called the face amount of the bond. It's also called the par amount or the principal. And usually bonds have a face amount of $1,000. So if you buy one bond, it has a face amount of $1,000. This So when you buy a bond, you pay D dollars today, and you receive the face amount at maturity. So as you can see, I'm trying to draw parallels between this box example where we had a box with $1,000 in it that gets paid in 10 years. Well, a bond is kind of like that. It pays the face amount some number of years later. Oh, this is the bond? Okay. So the way it works is you pay D dollars today, and then at maturity, the bond pays you back the face amount. And maturity is just the date that the face amount is returned. However, a bond also makes periodic coupon payments. And the coupon payments on the bond are just like interest payments on a loan.
How many accounts do you have altogether?
Generally, bonds pay semi-annual
Page
interest,
5,
or semi-annual coupons. So here's an example. If a bond has a face amount of 1,000 and a 5% coupon, then it pays $50 per year. Or more likely, since bonds usually pay semi-annual coupons, it will pay $25 every 6 months. And then it will pay the $1,000 face amount at maturity. And bonds are literally pieces of paper, just like money. And on the piece of paper, like Gary basically drew out here an example of a bond.
So here's what a bond might look like. Basically, you can see there's a section for each separate cash flow. So the biggest cash flow occurs at maturity, which is the $1,000 face amount paid on July 1st, 2013. So this bond, it has a maturity of July 1st, 2013, a face amount of $1,000, and a 5% coupon. And so each of these smaller sections here are the $25 coupons that are paid every 6 months. So the first coupon is paid 6 months from today. So let's suppose, for simplicity, that today is July 1st. The first coupon will be paid on January 1st, 2009. And it'll be $25 payment. And then 6 months after that, you'll get another $25, and the next 6 months another $25, etc. And then the last coupon payment is paid on the maturity date, which is $25 on July 1st, 2013. And so that last coupon payment is paid on the same date as the face amount. They're both paid on the maturity date. And and the way bonds used to work is you would literally cut off these little coupon squares and turn them in on the correct date, and you would get your $25 cash in exchange for your little coupon that you would cut out. So okay, hopefully that gives you a better idea of what a bond is.
Bonds are bought and sold in the market, and prices are quoted as a percent of face. So if a bond is traded in the market at 99.05, then the buyer would pay $990.50. That's assuming it's has a face amount of $1,000.
I know.
So you just take 99.05% and multiply by 1,000. In some markets, and I would actually venture to say most markets, the prices are actually expressed in fractions rather than decimals. And the convention is to quote the price in 30 seconds. So if the price is quoted as 99-08, that means 99 and 8 seconds, or 99.25%. So that's all I've got on bonds, but I figured I would put together a spreadsheet and have you guys watch me build it and then try to build something similar on your own.
Okay, so we've got Microsoft Excel open, and what we're basically going to try to do here is build a spreadsheet that will allow us to take the key details of a bond and use them to determine what the price of the bond should be. So let's see here. I'll zoom in a little bit so you guys can see better. And so we'll start by just typing in the key details of the bond. The face amount, which is $1,000. Oops. And all the inputs will color code as yellow, just so we know that, so we can separate the inputs from the calculations. Maturity is July 1st, 2013, which is 5 years from today. The coupon amount is $50 per year. Color code these as yellow. Coupon frequency is 2 times per year. And then this isn't an input, but we'll put it up here nonetheless. The coupon rate is $50 divided by $1,000, which is 0.05 or 5%. And then one other input that we're going to need is what the market interest rate is for a 5-year bond of this type. And we're going to assume, for starters, that the market interest rate happens to be the same as the coupon rate, and then later we'll relax that assumption. But so we're going to assume it's 5%. Add a few decimal places there. And by the way, depending on the context, the interest rate of a bond is sometimes called it's also known as the bond's yield, or the bond's rate of return. So those are basically synonyms. So now what we're going to do is lay out all the dates that are relevant to the bond. And that basically means all the dates on which a cash flow will occur. But for starters, let's type out today's date, which is 7/1, July 1st, 2008. And then the cash flows will begin occurring in 6 months' time. So the first cash flow is going to be $25 6 months from today, and then another $25 6 months after that, etc. So to list out all these dates, I'm going to use I'll show you a little trick using a series of Excel functions here, which are the day function, the month function, the year function, and the date function. So the day function, the way it works is you basically give it a date as an input, and then it'll spit out, in this case, the number 1, because July 1st is on the 1st of the month. If it were July 2nd, it would spit out a 2, July 3rd, it would spit out a 3, etc. And then the month function is similar. You give it a date, and it'll spit out the number 7, because July is the 7th month of the year. If it were August, it would give you the number 8, etc. And the year function, similarly, you give it a date, and it'll spit out the year. So in this case, 2008. And then the way the date function works is basically the reverse. It takes, you give it a year, a month, and a day, and it'll put those together and make it into a date for you. And the way we're going to use these functions is we're going to basically use it to add 6 months from the prior date to create a list of dates which are 6 months apart. So we're going to type date, and then this date is going to be in the same year, and the month is going to be 6 months after the prior date. So we're going to write month of B8 plus 6. And then the day is going to be the first of the month again, so it's going to be the same day. So basically what it does is it adds 6 months to the prior date. So it takes July 1st, 2008, adds 6 months, and you get January 1st, 2009. And then we can just copy this formula down. We get July 1st, 2009, January 1st, 2010, etc. And we can copy until we get to the maturity date, which is July 1st, 2013. Zoom out just a little bit here. Okay, I'll get rid of this. And the other thing that we're going to need is we're going to want to express the time that has elapsed in terms of years. So on July 1st, 0 years have elapsed, and every 6 months is basically half a year. So, on July 1st, 2009, 1 year has elapsed. All the way down, same thing, all the way down until July 1st, 2013, which is the maturity date, which is 5 years from today. And then we're going to start listing the cash flows that occur. And we're going to break them down into 2 columns. The coupon cash flows and the principal cash flows. So what I'm going to do is I'm going to center this across the selection, and we're going to make it bold. So we've got coupons and principal. So the coupons is going to be half the annual coupon every 6 months. So the annual coupon is $50. We divide it by the coupon frequency, which is twice per year, and we get that amount every 6 months. And then the principal, it gets paid in full at maturity. So that's $1,000 on the final date and $0 on every other date. And what I'll do is, just for the heck of it, I'll use a nifty little conditional formula to get us there. So if this date equals the maturity date, then the principal cash flow is going to be $1,000. Otherwise, it's going to be 0. So $0 until maturity, when the principal is paid back, $1,000 paid back on maturity. And then we'll sum up. We'll have a separate column to sum up these cash flows. We'll call it total CF for total cash flow. And we'll just take the coupon cash flow plus the principal cash flow, which on every date is $25 except for the maturity date, when the total cash flow is $1,025. Okay, next we're going to calculate the discount factors. Remember, the discount factor is what we use to multiply by the cash flow to get the present value of that cash flow. And in case you've forgotten, here is the formula for the discount factor. It is 1 over 1 plus the interest rate divided by the frequency, and then that quantity is raised to the frequency times the elapsed time. So for the first cash flow here, it's going to be 1 over quantity 1 plus the interest rate divided by coupon frequency, and then that is going to be raised to the coupon frequency times the amount of time that's elapsed. And oh, I need to freeze these. Okay. So there is the discount factor for the first cash flow. And then I should be able to just copy this down. So let's check it. It's 1 over 1 plus I2, which is the interest rate, divided by E4, which is the coupon frequency. And then that quantity is raised to the power of E4, which is the coupon frequency, times the number of years. So that looks right. Should be able to just copy this all the way down. So now each of these cash flows has a discount factor, and we're going to multiply each cash flow times the discount factor to get the present value of that cash flow. And you'll notice that the farther out in time you go, the smaller the discount factors get. That's because as you go farther out in time, the present value becomes less and less. Because you'd rather have, all else being equal, you'd rather have that money now rather than later. So a cash flow that occurs sooner is worth more than the cash flow that occurs later. And we'll see that when we calculate the present value here. So we're going to take the discount factor times the cash flow. And then we're just going to copy that formula down. So, for example, the coupon payment that occurs at the end of the second year is worth a present value of $22.65. And that final cash flow that occurs at maturity, it's a $1,025 cash flow, is worth only $800.73 today. Next thing we're going to do is, just off to the side here, we'll calculate the total present value. So now that we know what each of these individual cash flows is worth today, we'll sum them up to find out what the whole bond is worth in present value terms. So we'll take the sum of this whole column. What do you know? The present value of the bond is 1,000, which is exactly equal to the face amount of the bond. And I'll just point out, and maybe it'll make more sense later, that the reason that the present value is equal to the face amount is that the interest rate is equal to the coupon rate. That's when we go and change the interest rate around and make it different than the coupon rate, then we'll see the present value is going to change. But for now, we've assumed the market interest rate for a 5-year bond is 5%, and this 5-year bond happens to have a coupon rate of 5%, and so the present value of that bond, what do you know? It turns out that it's equal to the face amount of the bond. One more step here. I'm just going to convert that present value into a different formula or a different format to express it as a market price, and that's just going to be taking the present value divided by face amount and multiplying by 100. So now that that's all done, what we've done is we built a spreadsheet that allows us to type in certain the key features of a bond, and we also have to type in the market interest rate, and it's going to spit out the present value of the bond and the market price of the bond. So now that we've got the spreadsheet working, let's relax the assumption that the interest rate equals the coupon rate and see what happens.
So, what happens if interest rates go up to 6%? What do you guys think would happen to the present value of the bond? Before I show you, try to think a little bit about yeah, if I were to say the market interest rate is now 6%, what would the price of the bond? Yeah, it should. Do you agree that it should affect the present value of the bond? And so think about this. It's the sum of each of these present values.
Like individual ones.
Okay. So this is the discount factor times the cash flow.
The discount factor.
So what's right? The formula for the discount factor. That's also on the board if this is harder to read.
So is the rate the interest rate or the coupon rate?
The interest rate.
The coupon rate is fixed.
Exactly.
So you'd be multiplying by a smaller number, so it would go
Yes. Yes.
down. Right, that goes down.
Okay. So everybody agrees that it would go down. That's excellent. Do you agree with that? Okay.
You told me that.
Oh yeah. Um. So what's happening here? As the interest rate goes up, the denominator of that equation on the board gets bigger, and so it makes the fraction smaller. It makes the present value therefore smaller. Um. So each of these present values should go down. The sum of the present values should go down, which means the market price of the bond should go down. So let's see what happens. Interest rates go up to 6%. Voila. Present value of each of these has gone lower. The sum of the present values is down to $957, and the market price of the bond is now 95.73% of par. This is one of the, well, similarly, if interest rates were to move down to 4%, the present value of the bond would do what? It would go up. How much would it go up? It would go up to $1,044.91. And the price of the bond is now 104.49% of par. So, as interest rates go down, bond prices go up. As interest rates go up, bond prices go down. This is one of the just like fundamental facts that you should
memorize and understand.
People in the business for years keep saying, let's see, interest rates up, bonds down. How many people got to repeat that to themselves?
Oh yeah, I do that every day. Every day.
It's in the Wall Street Journal every day.
And yes, so the other thing is that if you ever forget, it's in the Wall Street Journal every day. I'll show
Why don't
you.
you turn that thing off? Turn that volume.
We go to the Wall Street Journal. Actually, we could probably see if you can find it in the print edition while I'm looking for it online.
Is this yours, Gary?
Every day there's a section of the Wall Street Journal on credit markets. It's in the markets section of the Wall Street Journal.
Marketplace or
Money and investing. Credit markets are the same. Credit markets are the same as fixed income markets. Fixed income market, bonds. Bonds are part of the fixed income market, so that's why we're looking at the credit market section. So credit markets today, the headline is Treasuries rally after solid auction. That means Treasury bonds rally, and rally means go up. So Treasury bond prices went up. So let's just roll through here. Actually, what I'm going to do is do a little search. And here it is. Here it is in the 8th paragraph. Says that bond yields move inversely to prices. And it literally says that every single day in this section of the Wall Street Journal. Just to remind you, in case you've forgotten, that when bond prices go up, bond yields go down. Any questions? Do you guys think that you can recreate this spreadsheet? If I help? Let's give it a shot.